it's my great pleasure to introduce our second keynote speaker, Professor Sonia Chernova. Sonia is an associate professor in the College of Computing at Georgia Tech. She's the director of the Robot Autonomy and Interactive Learning Lab. Sonia received her PhD and Bachelor of Science degrees in computer science, both from Carnegie Mellon University. And Sonia's research spans robot learning, semantic reasoning, human-robot interaction, and explainable AI, and she has done many influential works in developing robots that can effectively operate in human environments. And Sonia is a recipient of many awards, including NSF Career, ONR Young Investigator Award, and NASA Early Career Faculty Awards. And it's really exciting that Sonia is currently leading one of the National AI Institutes. So if you are not familiar about this, this is a AI Institute. It's a program with a significant investment from National Science Foundation, other government funding agencies to support long-term, high-reward AI research. So the AI Institute, led by Sonia, has a short name, AI Caring. The mission of the Institute is to develop collaborative AI systems that help support independent home life for elderlies, especially those with cognitive decline. So without further ado, let's welcome Professor Sonia Chernova.
Wow, thank you for that wonderful introduction, and thank you for the invitation to be here. Before I even start, I wanted to say I've been super inspired by all the talks so far today. They've just been amazing. The posters, the visiting researchers as well. So it's been such a pleasure to be here today and listen to the amazing speakers. So I feel very lucky to be here today. My work, so we've spent so far talking about making the world largely more accessible to humans. I'm going to turn things a little bit differently. I'm going to talk a little bit at the beginning about developing technologies that make the world more accessible to robots, right? How do we develop autonomous systems that operate in the world? But I will come back towards the end, towards this AI Institute that Joyce just mentioned, and talk about how we've been leveraging our work on autonomy in the context of humanity and starting to help, how do we help people, with everyday tasks. So, but first I'm a roboticist. I'm going to talk about robots first. But what drives my work in robotics, and was for the last over 10 years, is how do we develop autonomous systems that really go out and interact with the real world and with people. And ultimately, people are the big challenge, right? All the uncertainty in the world comes from people. We all find this world very comfortable. We can all navigate our own homes and do things there, but every single one of your homes is absolutely unique and presents a huge challenge to autonomy, right? We can field robots on Mars, but we cannot clean your bedroom or do your laundry. These are impossible tasks. And so over the last few years, I've been looking at how do we leverage semantic reasoning to achieve more robust autonomy, which is the kind of the topic I want to talk about today. What is semantic reasoning? How does it tie in a lot of really interesting research to me, and why to me, especially when you look at human environments, thinking about semantic data becomes really, really interesting. So that's what I'm going to start with, and then we'll transition to a little bit more of that healthcare aspect towards the end. So since I said semantic, let me introduce what I mean by semantics. It's an overloaded term, gets used in a lot of fields, a little bit different depending on who you're talking to. Here are a few visual examples from different areas of just computing, right? And so we could look at semantics of an object and segment objects into semantically meaningful parts, like the container versus the handle. If you're in computer vision, you might see something like this, a semantic scene graph, which doesn't just say, oh, there's horses in this picture. It actually tells you that these horses are Clydesdales, and they're not standing next to the wagon. They're pulling a wagon containing people, right? So now you have a relationship between the pixels, the objects represented by these pixels. Or we can take regions of space and maps and think about semantics there. I could fill this slide with examples, right? Lots of different examples, all of them under this classification of semantics. But if we were to just define what the term means, it's pretty much always a data abstraction of some sort, right? We start with XY positions, or we start with pixels, and we're trying to get abstract knowledge out of the meaning from that low-level signal. And that meaning we usually encode in the form of word labels, because we're humans and we communicate with each other with words. And so we put words on things like carriage and horse and pulling and so on. And this is a grasp affordance and so on. And so these words now encode concepts and facts or ideas about this low-level space. And to me, I already alluded to why I think this is kind of an interesting space to work, especially when you're talking about humans. Now I've taken low-level signal and abstracted it into something that humans use to communicate. And now I want to leverage this to start making this technology more accessible to users in the first place. So that's kind of where we're going to work towards here. As I said, my work and my students' work has largely been on kind of everyday environments. That's what really motivates me, just because I'm fascinated by the diversity, like the ease with which humans navigate everyday environments and how hard they are for technology. We've done a lot of different things to make autonomous systems more capable in these spaces. We've looked at object search. How does the robot find something? If I say, grab me a fork, you should not be looking in the living room couch. You should really be looking at the top drawer in the kitchen near the sink. Like, that's where most of us keep our forks. It's really interesting. We talk about object inference, which I'll talk about in a moment. But if you don't know everything about an object, can you infer its properties that you might not be able to tell right away? How do we use semantics to repair tasks? So robots often, all autonomous systems come with some sort of plan, or so they come up with a policy of how to execute certain process or task. Inevitably, things go wrong. Everything always goes wrong. How do we repair it autonomously using semantic reasoning and similarity between objects? We talk about semantic grasping, proactively assisting users and interacting with users and so on. So lots of different kind of very, very different applications, but to me, they all have a common thread of this abstraction of knowledge, right, into the semantic space. And so what I'll do today, I'm going to jump around. I'm going to talk about 3 of these areas briefly, and then move into how they connect to other work we're working on right now. Cool. So I'm going to start with object inference, which is like the most basic one here. And then we'll talk more about actually more towards the interaction space with users. But let's just talk about an autonomous system. No users yet. How does it reason about objects in the world, right? And the reason you need to do that is because to do any useful task for humans, you want to do laundry, you want to clean up someone's house, you need to reason about objects, right? So this is how we're going to get our robot butler. There's been a lot of work on modeling objects and semantic properties of objects. And why is there a lot of work in this community? For those of you, there's many people here outside of this research field, right? So robots have limited sensing. It's much more limited even than humans, and even we have limited sensing, right? And so you never know everything you want about any scene. A lot of facts are unknown and have to be predicted, right? But you have to perform inference, basically. And there's been a lot of work on representing, using different modalities, visual modalities, so camera data, tactile data, et cetera, to infer properties of objects, and also to infer affordances, which is if this thing is metal, what can I do with it? If this thing is glass, what can I do with it? Oh, this thing has a lid, what can I do with it, right? So a lot of this kind of reasoning. Now, what I want to talk about right now is kind of a very fundamental aspect of all the prior work in this area has been, despite the fact that it's all very, very diverse and very many different modalities, all of it has focused on binary semantic relations. Even though they actually contain a triple of information, but they're called binary relations. But because what it is, it's a binary relationship connecting 2 pieces of data, right? Cup is made of glass, true or false? Cup is made of ceramic, true or false, right? Cup has property fragile, true or false, right? And we collect huge, huge knowledge graphs, huge databases of these. There's standard data sets, right? And a lot of link prediction and knowledge-based completion research focuses on these large data sets, right? Consisting of these kind of triplets of relationships. And if you know some of them, can you predict the missing ones, right? So if I know that this cup is made of glass, can I infer that it's also fragile? Yes, usually yes, right? Those things go together. And so lots of representations, all using this kind of prior works. Our own work uses this binary representation. But the interesting thing about this binary representation actually is that it's not great. It forces the machine learning model to have to do quite a bit of work in order to make some of those predictions, right? So the analogy is the question I just asked, if I know a cup is made of glass, do I know that it's fragile? Yeah, I saw some people nod because those things are correlated in your mind. You've dropped enough glass things in your life probably that you've had to regret. That's one thing. If I show you this cup in the side of the kitchen cabinet, and I say, okay, is it clean or dirty? I'm guessing, hopefully 99.9% of you will tell me it's a clean cup. It would be pretty crazy to put a dirty cup in there, right? And again, we have very, very strong correlations based on prior data that, can we train a machine learning model to learn this from this kind of binary data? Yes, we can. If you have enough samples, right, you can do that. But turns out that there's another representation called n-ary relations that allows us to encode this kind of relationship more directly. So instead of having to learn it all entirely, I mean, you still have to do some learning, but it's actually a more efficient representation for semantic data because it explicitly represents the fact that certain pieces of information are interrelated. And so far, this is up until very, very recently, this type of representation really hasn't made its way into robotics, interestingly enough. We see it in some other areas of machine learning. And so, for example, here's a 4, n equals 4 way representation where we say, I have a cup. So this green information, this visualization that's supposed to show you green is what I know. Green, I have a cup. It could be in the sink or it could be in the cabinet. If I know that the cup is clean, and someone says, get me a clean cup, right? It's this representation that's going to fire. It's going to be the one that says cabinet that's going to, not the one that says, this representation says that dirty cups, ceramic cups are in the sink, clean ceramic cups are in the cabinet, right? And this is something that the model can learn. And if we can train a model, this is just kind of an abstract idea, but if we can, instead of going through these binary relationships, go to these n-ary relationships, we can more explicitly represent things that are more correlated. Cool. Now, if I have a robot, this is a fetch, I have a robot, I want to deploy it in a house, and I want to learn this stuff, I could program it to run around, drive around, and measure stuff for a very long time and observe, right? And it could observe just the way we do as humans, as kids. We learn that glass is fragile and we shouldn't drop it through our parents yelling at us and a lot of experience. We could do that with robotics, but we could also collect a data set, right? And so we collected a really cool data set that, as far as I know, is the most kind of diverse situated data set of objects. But I don't think I have a slide on the exact crowdsourcing, levels of crowdsourcing we had to go through to actually get this data set. We'll leave that for offline discussion. But we had people propose scenarios, and then there were other users who gave us excruciating details about various objects. But in the end, you get things like this is a blue cup that's out of thick ceramic. It's currently full. It's hard. It's at room temperature. It's in the sink in the kitchen, and so on. And so now we actually have a lot of situated knowledge about these different objects. And we can train a transformer, which pretty standard these days. A little bit less standard when we were starting to work with these models. And what we can do is train a model basically to reason about some subset of this knowledge, however much knowledge the robot has. And the really, really cool thing, I'll show you that in a second, about this model is the robot does not have to know everything. It can know one fact, it could know 5 facts about an object, and the rest will be filled in, right? And the way we train this model is if I have all of this data, I can mask out one piece of knowledge I want the model to learn about, right? And I can hide the location in the sink. I can give it all the other facts, and I can see whether it can predict sync. I could do that for other, in turn, all the other features here. But I could not just mask out one, I could mask out a whole bunch of them at a time, right? And so we can take each one of these examples and generate lots and lots of training data, which is thankfully very nice, so we don't have to have huge data sets. So we do this for all the different objects. And what we can do with that model once it's trained is be able to predict things that the robot doesn't actually know the answer to, right? So if I tell the robot, is a ceramic cup fragile? All I told you is the material of the cup, right? And the question is it fragile, right? And so by correlation, based on the data, it should be able to say, yes, where's a full and cold bottle likely to be located, right? These are the kinds of queries we want to be able to answer because we want to be able to have robots that assist people, right? And people are not good at telling you instructions like, hey, robot, could you get me the blue ceramic cup that's empty and clean on the top middle kitchen? No, right? It's not going to happen. People are just like, get me a clean cup or get me some tea, right? Even worse, because now you have to infer you got to have a clean cup to fill with tea. So you need an empty, clean cup. Where are you going to find it, right? And so this is kind of where this comes in terms of an assistive robot, is you're able to do it that way. The other way is it can sense, right? The robot's in the environment. It's staring at a cup hanging on this nice kitchen rack, and is wondering, well, I was looking for a clean cup. Is this it? Right? So this is kind of really cool. I'll probably skip over this, but if you're into transformers and things like that, you can start looking at attention weights and seeing how various features are predictive of different properties. So for example, material is very closely informative. It's very informative for the weight of the object, right? Certain materials are heavier and so on. So kind of a nice way to go in and make sure that semantically this all is making sense, which it is, and that's one of the nice things about semantic data. And so as I said, we have this large data set, 15 property types, 200 properties, 11 object classes. So we collected this very diverse data set called Link. It's available. And we benchmarked this, and the baselines we're comparing are all this. They're really state-of-the-art baselines, but they utilize binary relationships. Interestingly, I was kind of surprised that Markov logic networks are still performing as well as they used to. For those in the area, we've been benchmarking against Markov logic networks for, a good 8 years or something. And they're the closest baseline. But you can see in terms of both training time and runtime, they're incredibly intractable, right? They're really, really, really hard to scale to these anything of significant size. These more modern deep learning techniques are close in performance, and are obviously really fast. But going to an n-array representation is really, really helpful. We did one final little quick experiment, which was fun, which is to have a scavenger hunt and compete against humans. So this just to predict the location, nothing else. Humans are really good at this kind of stuff. But we did a scavenger hunt, gave them a house with lots of locations. We'd say, okay, where would you find a wet sponge? Where would you find a dry cup? Where would you do this? And everybody had 3 tries, right? So humans have 3 tries and algorithms have 3 tries. And humans are very good. So this dark blue is the humans, and the humans are better than AI. But I have to say, by the 3rd try, we're very, very, very close to human performance, right? But we're just, none of our systems are quite as good on the 1st try. Humans are just a little bit better at guessing on the 1st. By 2nd, it's a closer call, and 3rd, it's pretty similar. So that's a kind of an interesting benchmark for us, because it shows you that, because you almost want to, you say, oh, 88%, how good is that? Why isn't it 100? It just shows it's a really hard task, right? Because objects could be in a lot of places. This is not a task where necessarily 100% performance is something that's expected on the first try. You come to my house and look for a fork, you might not open the first immediate drawer, right? It might not be the first place you look, but you'll probably hit it in the top 3, right? And that's kind of what this data shows you. Yeah, any questions on this before I go? I'm happy to make this as interactive as people want. Yeah, Shawali.
So the NLE relationships that you're learning all from examples, from observation?
All from data.
Right, so I wonder how would we extend it if part of that information was coming in through language, because sometimes that's what happens, right? You go to someone's home and you ask them, where do you keep the clean mugs? And they say, oh, in this cabinet. So is there a straightforward way, or you would have to assume a symmetric sort of a symbolic?
Something else in the middle. I think you could do it. That'd be really interesting to try. We haven't tried it. My feeling is that humans are just not very precise, and that what a lot of our effort was just in crowdsourcing that data set was getting more information than people were really wanting to tell us. They're like, yeah, it's a blue cup in the sink. What more do you want? Right? But we're like, but is it room temperature or not? Like, tell me more about it. And they're very reluctant to actually put that into words. You can get it out of them. They know it. They just don't think it's very important. And we're trying to think about it from the sense of, like, what sensors do robots have, right? And if a robot finds a cup on the counter and it's half full, temperature might be an important indicator of whether someone's still drinking it, right? And we were just trying to think ahead to different scenarios. Yes, I think you could get all that data from language. I just think people are reluctant to be that verbose, right?
Understood. Yeah, that's fair.
Which is what makes this interesting, because I think once we can train on that verbose data, then we can scale back and follow instructions that are very, very minimal, and then potentially supplement them with the real-world sensors for validation. There's a really nice body of work. Tucker Hermans does some of it that pairs this kind of stuff with active perception, right? So if you're not sure about 2 answers, which perception action should you do to actually should you check the temperature of that cup to know whether it's clean or dirty, if it's vague, right? And so that's a really interesting body of work we're kind of aligned with. We good? Yeah.
Just had a question about the 3 tries that you have here.
Yeah.
So is there like independent tries that you get the top 3 decisions from the robot to see like where to look, or is it like you have a conditional like probability if the cup
They're ranked. Yeah, it's like ranked.
So the 3 most one, and then you just search for that 3. It's not conditional, right?
No, it's not conditional. Yeah, great questions. All right, so next I'm going to talk about, now that we can sort of identify object locations, object states, and so on, what can we do as far as helping users? This is work by Maithili Patel, who's a Michigan alum. She finished her master's here just a couple of years ago. Now she's a second-year PhD student in my lab. And here with her, we're working on helping people using a robotic system. And we're really making this distinction between reactive assistance and proactive assistance for an autonomous system. Reactive assistance is when you have to ask for help every single time. Alexa, set a 5-minute timer. Alexa, what's the weather? Alexa, okay, whatever your personal favorite assistant or none. This is always a push interaction, right? This is great for certain applications, but for a robotic system, it's actually, especially for the next several years, this is a problem. Robots are slow. I don't know if you've noticed. I don't know if you've interacted with a robot. Robots are painfully slow, okay? Robot, go get me a soda. Okay, I'll be waiting, right? And so it's really interesting to think about a robot that anticipates what you might need ahead of time, thinks about how slow it is, and gets you that thing before you even asked. Because what's the hard, if you screw up and it gets you your tennis bag and you weren't planning to play tennis, you say, oh, just put that back, and it goes slowly and puts it away. But it wasn't really, hopefully, very disruptive of your time, and items you wanted were there ahead of time. So we kind of are playing around with this idea of proactive assistance where you don't have to ask. And I'm motivated, originally we were motivated by the slowness of robots, and then I'll tell you later about some other motivations for why this actually goes well beyond that in terms of being useful. And so we had this idea of, okay, so how do we make a robot butler, right? We want robots to make us breakfast in this way. And we decided to make this really an object-centric approach. And what I mean by that is that we watch how objects move throughout the environment over time. Cereal in the morning, the cereal comes out of the shelf and goes on the counter. The milk comes out of the fridge, goes on the counter. The bowl comes out, this stuff happens. Then somebody eats stuff, then they put some of that stuff in new places, right? And the decision we made, which is a little bit, I think, controversial in some fields, is that we're not using any human activity recognition. We have another line of work on human activity recognition. It's really, really hard to recognize all human activities. Humans are very diverse. All kinds of stuff happens. So we said, why don't we just not even bother? Because honestly, it's kind of creepy to follow a person around and just watch them throughout their house. If you're a robot, that's kind of not nice. So we don't need to recognize each human action, because if we just know what happens to the objects, since the robot's going to be assisting by fetching new objects, that information is entirely actionable. Cool. And so we looked at a couple of prior works. There's two. Zhang et al. is, again, actually work out of Michigan, looking at static priors in order to identify how objects move over time. There's Krajnik et al. Also, which looks at some kind of temporal sequences, right? It combines time scales at different frequencies to predict how objects will move over time, right? So in the mornings, you tend to eat breakfast. In the evenings, you tend to clean up, like after dinner, right? And it just kind of goes by time of day. Now, each of these baselines has a little bit of limitation. For example, that second one only considers time. It doesn't consider the current state of the house, and to us, that's a problem. So we've developed a system that watches and considers the time of day as input, but also the state of the world. Right? And we spend we just watch first, and then we learn a model. This is using a graph neural network that takes in as input the current time and current state of the house and predicts the future state of the house some period of time into the future. Whatever, you can set that interval, and you can sample it at different intervals into the future, right? So you want to say, I want to know what it's going to be like in 5 minutes, and 15 minutes, and in an hour, or whatever. Right? And then based on those predictions, if they're considered high enough quality, the robot can go ahead and actually perform those actions proactively. I'm not going to talk about, I'm going to leave that for the paper. There's a paper that'll be presented this December that talks about the full architecture of this model, but basically the important part is that we're conditioning both on time and the current state, and we're representing those representations in the form of a graph. And we're predicting basically the edges of that graph, right? Where are the objects? What just happened? Where are the objects located relative to each other? We wanted a simulation to collect lots and lots of data. We could have done it in the real world. We're playing around with that right now. But we wanted a quick way to collect lots and lots of data. There's a simulator called Virtual Home that encodes avatars, and you can script them, and they interact with objects. This is a couple of videos of our avatars. Again, we had people come and write a whole bunch of breakfasts and a whole bunch of daily routines, and we kind of collected lots of information about how people do things and generated these fairly diverse, these are hard data sets, for how many, many days of data of activities would look like. So for example, this is one person. This is how, when they shower, they shower in the morning. Some people shower at night. This person showers in the morning. Usually right after brushing their teeth, but sometimes it happens a little bit later, right? And just something happened that day. And so there's kind of a lot of natural variability in that behavior. Breakfast for them is a little bit later, but once in a while they don't even eat breakfast, right? They just go to work. They're like, I'm not even hungry. So we have a lot of behaviors, some of which are easy to predict, like showering. Breakfast is a lot harder because actually this particular person only eats breakfast 50% of the time at most. Watching TVs for this person, again, is kind of hard. I'm trying to give you a few examples. We have easier people and harder people to predict, kind of a big spread. even if I was trying to predict this as a person, I would not have 100% accuracy probably on like guessing what you're going to do minute to minute. And so we want to develop a system that's robust. This is on purpose because we want to be robust to the fact that humans have certain behaviors that are more predictable than others, right? This is okay. And so what we want to use this model to do is to predict how objects move over time. And let me take a second to describe the Sankey for you. So we have all objects in the world, right? And I'm going to split them into those that were used by the person and those that just exist in the house, right? I have a vase of flowers. It's just going to sit there. I'm not going to touch it. It's just going to sit there for today, right? I'm not interacting with it. And then I have my breakfast bowl or whatever it is. I'm interacting with it. So these are categories where unused is much larger, typically, right? You don't necessarily pick up and use everything. And then out of the objects that are used, we want to predict as many as possible correctly that when they're used and where they're going to go. Like, when do you need it? Oh, you need your tennis bag by the front door. You're going to take your tennis bag. You need the breakfast bowl out on the table because you're going to eat with it. Oh, you have a dirty breakfast bowl. Let me put it in the sink, right? These kinds of correct predictions. We want as many of them. We want this number to be high. If we predict that you're going to use something, but I put it in the wrong place, that's bad. We don't want to do that. I take your tennis bag and I hide it and say, go, I know you're going to go play tennis. Let me hide this. That's going to be very, very bad. Less bad is just to leave it where it is. That would be OK. And then out of the objects that are not being used by the person, we also just mostly want to leave them alone. Hopefully, it's a very small number that we move around. Nobody wants to live in a house where things are constantly moving, right? That would be kind of weird. So these are kind of the numbers that should I unmute this? OK. All right, there we go. They wanted to be unmuted. And so here are some of our results. Against the two baselines that, again, I kind of have very limited time to discuss them in detail, but to kind of say that they don't consider as complex of a state in terms of time or current state of the environment. And what we see is we see a significant, this is a hard problem, but we definitely see that our model is really good at leaving things alone that shouldn't be touched. Which we made it a little bit conservative because we decided, okay, if you're not sure, if breakfast only occurs occasionally, just leave the bowl where it is. But if the model is able to predict something with high certainty, it actually takes action. And so we have a significantly higher correct destination accuracy, and we have basically we're lower on all the bad metrics and higher on all the good metrics. That's kind of the takeaway here. But it's been a really fun project to consider. How can we try to, without being asked about anything, just go ahead and guess what people might want. Okay, I'm going to come back to this. So if you have questions, hold them for a minute, and we can come back. I want to tie in one last project before I talk about other stuff, which is now that we're in this semantic space, how can we actually interact with users? This is the work of my student, Evelina Das. And in particular, going back to this idea of autonomous systems now doing stuff in our homes, inevitably, as much as we'd like, they're going to fail, right? You're going to walk into your kitchen and there's a robot standing there, and they usually fail by just freezing, right? That's how robots are. And so you come in and you wonder, what the heck is going on? What happened? Why are you just standing over my cereal? And how can I help with this? So the question is really, if you're not a roboticist, you do not have a PhD in robotics, right? You don't have any technical degree. If we take an average person and can we explain to them what went wrong and how to fix it? Okay. Now this is the intersection of these fields of robotics and explainable AI and a little bit of semantic reasoning. And explainable AI has been really hot in AI in general, machine learning, but it's just sort of slowly been seeping into robotics. So it's been fun to kind of play around. In terms of explaining how things break, that we had one paper, Devlina had one paper where we just started with, what do we have to explain? It was really a study on what do you put into an explanation, because that's how fundamentally underexplored this field was back in 2021. And we found out that people want context about the history of actions, and there's a variety of things. But then we kind of wanted to figure out how do we extract semantic context in a generalizable way. And I'll just show you one. What I like about this is really the results, but I'll show you very briefly what generates those results. So we're dealing with manipulation errors, so anything involving the robot arm, which all look very similar from a user standpoint. They all look like the robot didn't pick something up, right? And so you come in and the robot's not picked something up. And so what we're looking at is, can we use the visual scene and actually semantic scene graphs from computer vision to infer whether it's occlusion? Is it a motion planning error? Can we try to explain what is the cause? Is it too far away? Like, lots of different things can happen. We're not explaining hardware failures like, hey, my gear just broke. But this is more at the semantic space. And the cool thing is that we can take work out of computer vision, we can adapt it, we can train our own, use existing computer vision techniques to train semantic scene graphs that represent things like object occlusions, or one object being on top of each other, or too close to each other for grasping to likely work. And we can generate explanations. If you actually, just going very quickly, if you take these giant graphs and turn them all into language, that's actually way, way, way too much. What you want is to focus the algorithm onto just the most critical edges of this graph and generate explanations that look like this. So the robot could not pick up the can because it's occluded by the pitcher and too close to the cups. It might have been only one of those, but the model's going to say both. Here are some more examples of what we could say, right? The robot can't pick up the cell phone because it's under a book. Can't pick up the potato because it's occluded by a bottle and too close to a box of pasta. Can't pick up the grapefruit because it's too large to pick up. So now we're able to actually capture quite a variety, kind of just really simple system, just semantic, like scene graphs are kind of very standard at this point in image processing. And being able to connect this to something that ultimately the user interacts with was really interesting to me. And it's interesting from the following perspective. We ran a user study. I skipped a slide because it's easier for me to explain it here. We ran a user study where we first presented people with failure cases, and we asked what's wrong and how do you fix it. And then we gave them some explanations, and at the end, again, gave a post-test on new scenarios. What's wrong and how do you fix it? Now, they saw 16, I think in 16 scenarios, before and after. And if you provide no explanations in between, people improve slightly over time, right? That's the fact that this has a positive slope. People get better at guessing what's wrong and how to fix it, just because they're humans and that we're amazing machine learning machines. But if you start to provide a little bit of explanation, people improve better, right? And these are so this is SSG. This is the full, it's actually overwhelmingly long explanations. I actually didn't bother reading them out because they're a little bit of a pain to read. They're things like, I can't pick up the can because it's next to the thing and on the table and behind this thing. They're kind of exhaustively long. And humans eventually find patterns in those long chains of words, but not easily. But if you actually narrow it down to just the most critical relationships in those, the most critical semantic relationships in those graphs, suddenly people get it, right? This is so simple from our machine learning standpoint. I'm not here saying, oh my God, we found a new machine learning technique. What I'm saying is we can take a really well-established, understood semantic learning mechanism and use the fact that it abstracts these concepts into an accessible, like really accessible way to communicate with users, that we can now make people be able to understand what's happening with their system, this big black box. And it's so simple that it seems like cheating, but it really, really works. These results so far, these are on idealized scene graphs that we coded by hand. Let's see what happens when we actually code them using code, because scene graph algorithms have a little bit of an error rate. And finally, this is statistical results. But humans don't care that much, right? They're really not sensitive to small errors in these scene graphs. This works even with real data, not hand-coded data. Just really blew my mind when I saw this. I really like how simple it is and how it allows us to communicate with users. So again, just wanted to share this one. This to me, it just kind of seems fun as far as leveraging semantics for communication. Now, okay, big picture is that I've been talking about robots, and I promised I wouldn't only talk about robots, but I'm really curious about how robots can assist people in homes, right? But lately, we've been thinking about other applications, and to me, even as a roboticist, we can go back to that whole discussion of what exactly is a robot, right? And sense, plan, act is the usual answer. But what if we have other modes of interactive AIs in these home environments that can also provide assistance? What does that start to look like? So do we have to have all of our sensors on this thing, or can there be sensors spread throughout the house that also make the house more of a robotics? Can you live inside a robot, right? And there's a lot of people working on smart homes. And that brings me to this NSF AI Institute that I just wanted to mention briefly, since I know a lot of people here are also thinking about the AI institutes of their own. Ours is called AI Caring, and it's a partnership with a lot of really amazing people from Georgia Tech, Carnegie Mellon, Oregon Health and Science University, UMass Lowell, and Oregon State University. It's a really big group. And what we're focusing on in 5 years, we're just kind of in the early stage of those 5 years, is developing interactive systems that interact with users over very long periods of time, months and years, right? So how do we think about interaction that can understand your behavior over a much longer time period? And a lot of this is through devices that already exist, home sensors, interactive voice assistants, network devices, a little bit of robotics. So yeah, a lot of stuff that already exists. It's not so much developing brand new sensors, but about integrating them and making that interaction meaningful. And our target population is one we're really excited about. It's individuals with mild cognitive impairment, MCI. It's a precursor to dementia. It's a really interesting use case because Alzheimer's, dementia, we all know those diseases. And we've all know that at some point, you really need a lot of assistance and support. MCI, a lot of folks are still independent. This is early stage stuff. But they're, depending on their progression and stage of their diagnosis, they're really being supported at home. It's too early for assisted living. They're living at home independently. But it takes a huge toll on their family to really, their spouse, their children, to support that independent life as long as possible. And so we're working with these individuals, but we're also working with their care partners, their family and friends, to whom this is like a second job, right, is helping this individual manage their condition. And so our goal is, in the development of these conversational smart home assistants and a little bit of robotics, to help sustain independence for the individual and then also support their caregivers. From an AI perspective, we're doing learning models of human behavior, anomaly detection, right? Understanding change. Abrupt changes are actually relatively easy. It's the slow, gradual change that's from a machine learning perspective a lot harder. And then a really hard problem of how do you provide coordinated assistance across this care network. So, our team is basically a lot of behavior modeling, NLP, dialogue systems, multi-agent coordination. And every aspect of this is research. So you think speech and dialogue is, doing pretty well? Try running it with somebody who is, 85 and 86 years old. It's a very, very different population. The way they talk a little bit is very, very different. We, in our current deployment, have a family who's very sporadic about using Google Home, and we asked why. And she said, well, after 6, I don't bother it. Google goes home at 6. So I didn't want to ask. And we were like, well, Google doesn't go home at 6. But that never occurred to me to explain that Google doesn't go home. OK. So, really fundamental stuff, let alone how you ask Google and how polite you should be when you ask Google things. And as you know, if you interact with dialogue systems, the more complicated that sentence, the less likelihood you're going to get an actual reasonable answer out of the AI, right? So lots and lots of huge challenges. Going back to like our little problem that we started with here with doing proactive assistance with a robot, we're now looking at how do we take that technology and also use it in other applications, and particularly with folks who are having a lot of memory issues. The fact that we can learn their personalized schedule over time and monitor it also means that we don't have to take over tasks for them unless they really want to. That's actually up to their clinicians. But for many people, they might need a little bit of a help remembering to do things. And that might be remembering to take their medication, which you've probably heard of. What about remembering to eat? Yeah, that happens, right? And what about remembering to put the milk away so it hasn't been sitting on the counter for 3 hours before you drink it next time, right? So these like literal health issues are a major, major factor. And so we're working on some of those. And also alerting care partners when there's big shifts in behavior, of course, or things are being done or done too many times and so on. And this is kind of in partnership with lots of clinical folks as well. One lovely thing about collaborating with people is, to me, just the fun of the collaboration, but also that you get to look at really, really cool data. I did want to mention that I think for AI, the healthcare community, as many of you know already from the speakers today, have absolutely amazing real-world impact data that a lot more of us computer scientists, I think, should be looking at. We're working with OHSU to work with they have 1 to 3 years of data they've instrumented hundreds of homes and just collect behavioral data, what happens. It's a really hard data set to work with at the moment because it has no ground truth. So we're working with them to consider how to fix that. We have 28 deployments in Atlanta that we do manage much more closely than that, and we have a few others. We have access to over 50 individuals, basically families of people with MCI and their care partners who are really involved in our research program, which is really fun. And we can talk to them weekly pretty much in these think tanks when they exchange information. The students can come and pitch ideas and kind of get feedback on research. So that's been really interesting. And then a lot of audio data. If you're interested in kind of language and dialogue and some of the speech stuff I mentioned, the clinical community has collected tons of data of how people speak as they age. Particularly with Alzheimer's and MCI and dementia, which is also really, really interesting. So kind of acting here is a little bit of a facilitator. If you have any interest, some of this data is hard to get, and we've worked very hard to get it, but we can help provide access to others or facilitate access. That it's not always easy. But if you're interested in that kind of data, please reach out. I think it's kind of been really interesting for us, and I think a lot of it is not widely known in the community. And behind me on this effort is a huge, huge team of really, really cool people. So just wanted to give them a shout out. And with that, I'm going to open it up to questions. I tried to keep things on time. And I want to thank my students who are really behind all of this work. Mainly, I presented the work of Wayu, Devlina, and Maithili. And yeah, I'll take questions.
Yeah, great. Thank you, Sonia, for this fantastic talk. So we have time for a couple quick questions.
Windows start.
Yeah, thank you for the great talk. It's a really awesome vision, and the scope is really exciting. So I have a question about the object-oriented representation. How do you think we should resolve the gap between how humans talk to robot and then the object-centric representation? So my point is, sometimes I think human talk to robot more through activities. For example, grab me that cup of coffee or make me a breakfast. But if you only monitor the object movement, maybe I only drink a coffee for Monday to Friday for breakfast, but then during the weekend I eat a full breakfast. Then tracking the object, would it be sufficient to map it back to the activity that human used to refer? Yeah.
That's a great question. So I think there are definite limitations that now would be a good time to mention of only an object-focused approach, right? And one of those limitations is that while we could handle weekends being different from weekdays, that's not an issue. But there is an issue that it's a little bit harder to adjust if the person does do something unusual, right? If I decided today was the day I was going to eat breakfast early or have a full breakfast instead of a small breakfast, if I could recognize that right now, then the robot would maybe not bother taking out the cereal later, right? Things like that. And so we're currently assuming you can infer that through the current state of the house, but that's a little bit tricky. So I think the answer to your question is that in the long term, I think we want to combine the strengths of both activity recognition and object modeling. And I didn't mean to misrepresent that. I definitely do think there's a place for activity recognition. The reason I want to start with objects only is because it's really tempting to condition everything on activity labels. And it's really impractical to assume that we always have activity labels, because we don't, right? It's a really lossy, imprecise signal. So kind of coming at it on purpose from a different angle. But as far as human communication, you're right. What I would like to do is connect the first project and the second project, where human instructions can be very, very underspecified. And we use kind of what's called link prediction, right, or knowledge-based completion, right, techniques to infer the missing data in those instructions. There's a lot of work on that kind of vague instructions and grounding vague instructions, right? So kind of connecting a lot of those fields.
Okay, so I have a question too. So I'm a big fan of a semantic processing, using the semantic as the basis to communicating with the robots, because that really bridge human and agents. But when we submit works like this, some of the reviewers, because that requires some sort of a domain or knowledge engineering, and then the reviewers often would get back to us saying something like, okay, how do you address this kind of engineering effort? And what if you bring your system out of completely novel environment? You don't have any of these semantic aspects, identified, modeled. How do you address that, right? I think that's a fair question too. So I just want to, wondering. What's your thoughts on, how to bring these semantic-driven kind of approach to more open domain, novel situations?
I think that's a really great question. It's tough, right? And especially in the world of big data, when the semantic knowledge databases we want we can work with or easily work with are huge. I think that we need to develop more techniques that mine this kind of data through interaction, and there are some kind of a little bit in that active perception space. I don't see why the data can't be gathered in a novel environment. There's no way to skip that. Either you have no semantics or you have to get them, right? Okay. I think we can develop systems that gather that information to some degree. I say that because there are certain things that are really hard. We've worked with the Navy. We've been funded by the Navy for semantic reasoning. And you know what? Maintaining submarines is a very specialized skill, and even I can't write the semantic knowledge base for how to maintain the valves on a submarine. And extracting that data out of experts is really expensive. So that's where we hit a brick wall, right? You either want to say, okay, I've got enough resources to devote to actually this problem, or you say, no, just keep working on something else. I don't have a magic answer, unfortunately, I think.
Yeah, that's that's a really interesting direction to pursue. So that's I mean, for interacting with the robots, this semantic reasoning really playing an important role. I love all the results you've shown there really demonstrate that kind of effect. So any other questions? If without questions, let's give another round of.
There's one over here.
Oh, sorry, didn't.
Yep. Thank you for the great vision. I really enjoyed, like, especially the final part. Like, the envisioned future seems really promising, exciting to me. Like, I'm having one question on the continual learning part of the final envisioned version of the human AI long-term collaboration. Because I do see a lot of your work in like focusing on current interaction between human agent and like a daily based, like periodic temporal constant like interaction. But like I cannot, like at least for the moment, I cannot imagine like what if the human's behavior adapt through like a long term throughout the time. And like I was just wondering what's your thought on this like multiple timescale based continual learning on human AI collaboration. And do you think that's a challenge, or do you feel like what are some approaches towards that?
Yeah, I don't think we have answers right now. It's a huge challenge, right? Is how do you actually take this to meaningful long-term interactions? Because we as a field have not really studied that in this kind of space. I think in our use case, a lot of those interactions have to do with the distinction between there's certain interactions for things we want to maintain routines for. We're either trying to maintain routine behavior or we're trying to address anomalies. Those are the two, when we work with clinicians, that's the two things they hammer on, right? They say we want to maintain good behaviors, we want to detect and stop wandering, spam calls, and what was their third one? Certain dangers involving cooking, right? Those are the three big things that land someone in assisted living. Well, and there's a fourth one, falls, which we can't prevent. They really, really want us to prevent spam calls, by the way, in case anyone has a solution for that. It's a huge issue. But those are the four factors that kind of really make that change. So anyway, going back to your question, I feel like in terms of interactive techniques, those are the two focus areas. Identify things we want to happen and try to make them happen, try to sort of support their independence of someone and maintain those behaviors, or detect abrupt or slow gradual change and try to mitigate that change or make people aware of it. And a lot of times the technology is not there that it can mitigate itself. We're not going to cure MCI. I'd love to, but we're not, right? But we can partner and alert clinicians and make them aware and give them access to data that they otherwise would never have, right? So
Great, thank you.
Yep, thank you, everybody.
Thank you, Sonia.